All right, let's just jump right in. Modern biology, it's just a world of data. I mean, we can now measure thousands, sometimes even millions of different things inside a living organism all at the same time. But the real question is, how do we turn that absolute mountain of information into actual useful knowledge? Well, today, we're going to crack that code. And when I say a mountain of data, I'm not kidding. Just think about it. You take one tiny little sample from a lab mouse. That single sample can spit out a spreadsheet with millions of numbers, where every single number represents a different molecule. It's just an unbelievable amount of detail. So that's the real million-dollar question, isn't it? It's kind of like trying to hear a single person whispering in the middle of a roaring football stadium. How on earth do scientists sift through all of that noise to find the handful of molecules that are actually changing, the ones that are telling the real story of what's going on? To get our heads around this, let's look at a classic scientific mystery. Let's call it a tale of two mice. We've got two groups. One group is just eating normally, business as usual. The other group, they've been fasting for 12 hours. And what we want to know is, on a molecular level, what exactly changes inside their bodies? This is what you're up against. This is the raw data. Each row here is one of our mice, and every single column is a different molecule that was measured in its liver. Just look at it. Staring at this, it's completely impossible to see any kind of pattern. It's just a wall of numbers. So, we need a special kind of tool to help us see the bigger picture. So the first tool in any data scientist's toolbox is a method that's built to find the biggest, most dominant patterns in really complex data. It's called principal component analysis, or just PCA for short. You can think of it as a way to kind of zoom out and finally see the forest for the trees. And here's what happens when we run that data through PCA. And voila, just like that, the data points snap into two perfectly neat clusters. Over on the left, you've got all the normally fed mice, and on the right, all the fasted mice. So we've done it. We've proved a real, measurable difference exists between the two groups. Mystery solved, right? Well, not so fast. And this is where things get really interesting. See, that PCA chart is fantastic for telling us that the groups are different. But it doesn't tell us why. Which of those hundreds and hundreds of molecules that we measured are actually responsible for creating this separation? What's the cause? To answer that why question, we need a totally different kind of lens. We need a magnifying glass. We need to look at something called loadings. This is the tool that lets us zoom right in on the specific culprits that are driving the change. So PCA really gives us two key pieces of the puzzle. The scores are what we just saw. They confirmed that our groups were different by creating those separate clusters on the chart. But the loadings, that's where the magic is. The loadings tell us why, by pointing a finger directly at the specific molecules that are most influential. So, what even is a loading in plain English? Well, you can just think of it as a number that tells you how strongly each molecule is connected to the separation that you see on the chart. So if a molecule has a really high loading, it's a major player. It's one of the key reasons the fasted race looks so different from the fed mice. For years, calculating these loadings in a proper, reliable way was a huge headache for scientists. But now, there's a standardized toolkit that makes this incredibly powerful analysis accessible to pretty much anyone. It's a software package for the R programming language, and it's simply called Loadings. And this package is an absolute beast. It does so much more than just basic PCA. It gives you standardized, trustworthy ways to find the key molecules, even in really complicated scenarios, like when you're collecting data over a long period of time, or when you have to combine totally different kinds of biological information. Okay, so now that we have the toolkit, let's really put it to the test. We're going to tackle two real-world puzzles where this new approach uncovered some breakthrough answers that were just completely hidden in the noise before. Okay, first up, a study on yeast being used to produce biofuel. Here, the samples were taken at a bunch of different time points, from hour 0 all the way to 96 hours. When you run a standard PCA on this data, you get, well, this. It's a total jumble. You can't see any clear path or progression over time at all. But now, look what happens when we use an advanced method from the loadings package called smoothed PCA. It's the exact same data, but now it's beautifully organized into this smooth, elegant curve that clearly shows the metabolic journey the yeast went on over time. It literally transforms chaos into a clear story. Okay, that was impressive. But what if your puzzle is even more complicated than that? what if you have data on proteins and you have data on metabolites from the very same patients, and you have to somehow combine them to understand a disease? Well, this exact challenge was front and center during the COVID-19 pandemic. Scientists had these massive data sets on both proteins, the proteome, and metabolites, the metabolome, from patient blood samples. The problem? They were like two separate stories, written in two different languages. But there's a specialized tool in the Loadings package that can actually weave these completely distinct data sets together into one single unified picture. And this is the result. This single chart, which combines those two different omics datasets, perfectly separates the healthy people from those with mild COVID and those with severe COVID. It creates this clear, ordered progression of the disease. And this is the kind of insight that can lead to brand new diagnostics and treatments. It's huge. So, what does this all really mean? Let's take a step back. We've gone from staring at a confusing wall of numbers to having a clear, actionable understanding of biology. And this is the fundamental shift right here. We can finally move beyond just seeing patterns to truly understanding the specific molecules that are driving them. It's the massive difference between knowing what is happening in a disease and finally beginning to understand why it's happening. And this leaves us with a really fascinating thought. We are getting better and better, exponentially better, at generating data. The real bottleneck now is our ability to make sense of it all. So as tools like the Loadings package give us a better way to look, you just have to wonder what other incredible breakthroughs are already there, hiding in plain sight, just waiting for the right lens to finally bring them into focus.